So in section 12.2, we're kind of bumping things up a level from section 12.1. In 12.1, we solved 2x2 systems of equations. Now we're going to solve 3x3 systems of equations. So 1, 2, 3 equations in 1, 2, 3 unknowns. Now a solution for a system of equations like that is where these three planes intersect. And one thing you might be asked to do is decide whether or not an ordered triple, sometimes I call these a three-tuple, is a solution to this system of equations. Now what that would entail would be plugging in your x, y, and z, or if these are other variables, r, s, and t, a, b, and c, whatever, into the system of equations and see if they satisfy it. So this point has to work in all three equations. Let me start with the first one. So -2 for x, 1 for y, -3 here. That turns this into -8 plus 1. Minus and a minus is a plus. So +3. And I'm not thinking that that's equal to -8. So this one is false. Doesn't work in that one. Do I need to check the other two to find out whether or not this is a solution? Is it good enough to work in 2 out of 3 of these, or does it have to work in all 3? What do you think?
All 3.
Yeah, it has to work in all 3. So this is not a solution. For the most part, though, you can probably expect to actually try and solve these things rather than to test whether or not something is a solution. This is a good idea once you're done with the problem, is to go back and make sure that it works in all 3 equations, but it's not a method that we're going to actually use to try and solve these things. You can't just check a bunch of random numbers. There's a triple infinity of those things. So how do we do that? How do we solve a system of equations? Well, one of the systems of equations that you have in your homework looks something like this. Now, when I used to teach this back when I first started, I thought, hey, I'll give them an easy one. I'll give them one like this. But it's confusing. And I've learned a little bit about why it's confusing. And that's because they didn't take the time or patience to write something here that's missing, and that is a y. So I'm actually going to take time and at least account for that with a space. It's going to be x plus 6z equals -54, and then 5x plus 3y minus 2z equals -14, and y plus 4z equals -32. All right. And the only benefit of that really is that it makes it a little bit clear that I'm missing a y from the first equation and an x from the third equation. The way I suggested in my other video that we solve these things is you pick one equation and eliminate a variable from the other 2. Now, I'm already missing an x here, so if I could somehow get rid of an x from another equation, I'd be in great shape. And I did suggest that you try and pick equations that have a coefficient of 1 or -1 as being easy to deal with. So I'm going to pick this first equation and see if I can't eliminate the x down here with this equation. So how could I do that? What could I multiply this by and add it to this equation so that I can get that to cancel?
-5.
Yeah, thanks, Michael. So it'd be -5 times row 1 added to row 2. So -5 times that would be -5x minus 30z equals 270. And I'm going to add that to row 2, so just copy that there, 5x plus 3y minus 2z equals -14. So I get what I expected. I canceled out the x's by doing this. Those disappear. And I'm left with 3y minus 32z equals 256. Wow, did that really help me out much? Well, I claim it did, because if you look, I've got this equation here and this equation here that both depend on y and z. Now, it's important that you have two equations that have two unknowns, the same two unknowns. Doesn't do me any good to have an equation that's missing a y here and an equation that's missing an x here. I need two equations with two unknowns. So let me put those together. It's y plus 4z equals negative 32, and 3y minus 32z equals 256. So that's a 2x2 system, two equations and two unknowns. You're free to solve that any way you want. You could solve it by graphing, you could solve it by the addition method, you could solve it by substitution. In this case, I'm going to solve this one by substitution, but like you said, there's a lot of different ways you could solve this, and whatever you want to do, you need to find what y and z are that match or that solve this system of equations here. Probably the easiest way to do this by substitution is to move this to the other side and get an expression for y. So if I move that to the right-hand side, I get y equals what? Can anyone tell me?
Negative 4z plus 32. Or no, minus 32.
Perfect. Negative 4z minus 32. Now, the good news about that is that now I've got this expression here. I can plug it in for z, or excuse me, plug it in for y right there. And that'll allow me to solve the system of equations. So it's going to be 3 times that expression minus 32z equals 256. So that y there can be replaced by negative 4z minus 32. Now that's nice because this equation just has one variable, right? It's a z. We started out this semester by solving linear equations and inequalities. So this brings us back to something that we've done before. I can distribute the 3 here and get negative 12z minus 96 minus 32z equals 256. Probably what I would suggest first is that we combine like terms. So I can combine the z's here and get negative 48z minus 96 equals 256. We want to solve for z here. So let's add the 96 to both sides. That gives me negative 48z equals 352. If I divide both sides by negative 48, I end up with z equals negative 8. That is part of my solution. Yay. Am I all done with that?
No.
No, you're right. We need to go back and figure out what y and x are. Now, the good news, at least for y, is that I can take this and put it right there because I've got y defined in terms of z. Y is giving negative 4 times z minus 32. So If I substitute that in, -4 times -8 minus 32 gives me 32 minus 32. Can someone pull out a calculator and help me out on that one? What does y equal?
0.
Yeah, thanks, Michael. All right. I was trying to give people a chance to get their calculators, but all right. 0. So 2 down, 1 to go. I still need to figure out what x is. But I can't figure out what x is by going back to these equations because they don't have an x. So, all right. Let's go back. We got to use one of these two equations, the first one or the second one. I know my favorite, but it's up to you. Which one should we choose? First one or the second one to help solve for x?
The first one.
Thank you. Yeah, the first one all day. First one's looking a little bit more user-friendly. So that the equation was x plus 6z equals -54. And I know what z is. Z was -8. So that gives me x minus 48 equals -54. If I add 48 to both sides, I end up with x equals -6. And so that's another piece of my solution. In fact, the last piece of my solution. Now, typically, you write these in alphabetical order, x, y, and z. And this is what you'd have to put into WebAssign. You'd be putting in -6, comma 0, comma -8. Don't worry. I won't put any more than 20 of these on the next exam. Let me back up and kind of review things. We just cleaned this up the way we wrote it, and that showed us that we're missing a y here and an x here. So we decided to use this equation to eliminate the x. We did that, got rid of the x, and now that gave us two equations that just depend on y. The two that I have circled, excuse me, depend on y and z. The two that I have circled here in yellow. We put those two together. You need to solve this any way you want. Now, when we solved it, we ended up with 0 and -8 for y and z respectively. But you're able to solve this any way you want, and that's fine. So once we solve that, we solved it by substitution. We got z equals -8. I put that back in this expression for y to get y was 0. Once I had z and y, we went back up to the top, plugged in the value for z. There was no place to plug in a value for y. Plugged in the value for z, and we solved for x. Yay. Now, if you're really conscientious, you'd take the time to plug this into all three of these equations and make sure that it works. For instance, -6 plus 6 times -8, well, it's -48 plus -6 is -54. It checks, and so on. It should work for all three of these equations. If it doesn't, there's something wrong. Figure it out. Whew. All right, take a deep breath. We've got one more here.
I had a question.
Yeah, Abby.
So can you go back to the last page just so I can show you?
Yeah, sure.
So like when you start off on it at the beginning,
Yeah. Mm-hmm.
you know how you circled the one in yellow with the y plus 4z?
Yes.
Would you have used that as the like starting equation because the y is by itself, or would you have had to use the one you circled in blue?
I guess it depends on how you're going to do it. I mean, if I was going to use this equation, what I'd probably do is use this equation to get rid of the y from this equation. And then I would have had two equations. Let's see, would that have worked? No. Let's see. Boy, other ways you could do this, let's think. So if I wanted to, yeah, I suppose I could use this equation to get rid of the y from this equation. So if I multiplied this equation by -3 and added it here, I'd have an equation that had x's and z's, and then I'd use the top equation and whatever I got by manipulating this one. So I'd have something that had x's and z's in two equations, and I could solve it just like we did here. So it's not the only way that we did it, is not the only way that you can do it. There's a lot of different ways you can approach this. But, yeah.
Pick like a variable that was, I didn't know if you had to.
Yeah, so the convenience of picking picking the x here is that I already had an equation that didn't have an x in it. So all I had to do this step once. I multiplied this by -5, I get rid of the x here, and then bam, I've got two equations that have the same two unknowns. Now, it's certainly possible if you wanted, you could have picked the middle equation and gotten rid of the z's here. That's not too hard. If you multiply the middle equation by 3 and add it to the first equation, you can get rid of the z here. Multiply the middle equation by 2 and add it to this equation, you get rid of the z here. And then you'll have two equations that have x and y, and you can solve that. The difference is I have to do this kind of step twice to get rid of the z's from both of these equations, whereas choosing to get rid of the x's, I only had to do that step once. So it saved me some work, is the way I see it.
Oh, okay.
Does that make sense though? Eliminating the z's would be two steps. You'd have to eliminate it from here and here. Eliminating the x's, I only had to do that once. So that was the benefit of eliminating the x's.
Yeah.
So yeah, if you're careful about these things, sometimes you can make yourself, save yourself some work. But I wanted to do this one because it's confusing. And I get it. People are seeing these different variables that are missing from different equations, and it gets confusing. The overall goal is to get rid of the same variable from two equations, like we're going to do here. So we are going to get another one. In fact, let's see. For my morning class, we got rid of the z's. So we picked an equation. I think the middle equation, we got rid of the z's from the other two equations. But the thing that you need to look for is to, pick something with a coefficient of 1 or -1 is typically the easiest. So I could pick the y from the third equation or the x from the second equation and use those equations to get rid of a variable from the other two. Let's see. Yeah, so here's what happened when we got rid of the z's. I chose this equation, got rid of the z here, and got rid of the z here. And so that gave us these two equations. We'll end up with the same solution, even if we choose to do it a little bit different. So let's do it a little different. I'll give you a choice. Do you want to use this equation and eliminate the y's, or this equation and eliminate the x's? Your choice. All right, the x's have it. If I choose to eliminate the x's from these two equations, let me start by getting rid of the x's up here. So what would I multiply this by to get rid of that x?
-3.
-3. Now, it's not necessarily a requirement, but it helps me out immensely when I grade your papers to see stuff like this. -3 times row 2 plus row 1. You just label it so I can see what you're doing, and it helps me catch mistakes and makes it easier for me to give you more partial credit. So that'd be -3x plus 6y minus 3z equals 36. And to that, I'm going to add 3x plus 4y plus z equals 46. And that's going to give me a total of 10y minus 2z equals 82. And just leave that one there for a moment. You've got to do this procedure twice because I need two equations with these same two unknowns. So that's why we're going to get rid of the x down here. -2 times this row added to row 3 would be -2x plus 4y minus 2z equals 24. Added to 2x plus y plus z equals 15. For a total of 5y minus z equals 39. Okay. This is what we wanted. You've got two equations with the same two unknowns. So let me put those together. That's a little 2x2 system. And this time I think I'm going to solve this one with the addition method. Seems like it's going to work out pretty good. Oops, that should be just AZ. Can anyone see how to solve this pretty quickly with the addition method?
Yep. Type 2.
If you multiply the bottom equation by -2, let's see what happens. So we'll multiply this by -2 and I'll add it to that one. I get 10y minus 2z equals 82. And then -10y plus 2z equals -78. Oh, boy.
Professor Parent, I do have a question.
Yeah.
Okay, so it's kind of going back a couple of steps where you had selected, well, based on the recommendation to select a coefficient of 1 or -1.
Mm-hmm.
You selected the x minus 2y plus z, and you multiplied that by -3.
Correct.
Maybe I got my.
So I'm using this one to eliminate the x's.
Right.
So,
and so you would have multiplied it by -3, right?
Yeah, multiplied by -3, which is what I have here.
Okay. Alrighty. Thank you.
Had I chose the y to get rid of the y up here, I'd multiply by -4, but to get rid of the y here, I'd multiply this by +2. So
Gotcha.
You know, it's going to change depending on what you select. But what won't change is your solution. And the solution that we get down here, well, you tell me. Somebody help me out with the left-hand side. What do I get when I add those together?
It's going to be 0.
0, thank you. And on the right-hand side, I get 4. Uh-oh, that's not looking good. Does 0 equal 4?
No.
No, it doesn't. And so what's going on here is that these planes don't intersect at one point. There's no solution. Now, no solution is not what you're going to write for your answer here, because there's a mathematical term that describes this situation. Does anyone remember what it is from the video? Starts with the letter I.
Inconsistent.
Inconsistent. Thank you so much. Inconsistent. That's what you'd say about this. Basically, these three planes don't intersect at the same point. And even though I did this a different way in my morning class, I still ended up with the same conclusion. So we chose to eliminate the X's there. No, let's see, did we? No, I guess we did. I guess we did do it the same way. All right, my bad. But had we chose, to eliminate the Y's, you still would have ended up with something like this, something that's not true, and all the variables have dropped out. And if you get to that point, then you've got an inconsistent system of equations. All righty. Comments or thoughts on that one? Let me get you in some groups here and get you started.